I will start today's class. Hello everyone, I am Honato, PhD scholar at IIT Kanpur. Today I will review of week 7 of fundamentals of supersonic and hypersonic flow. In this week, mainly the kinetic theory of gases, vibrational non-equilibrium and chemical non-equilibrium was taught. Most of the content for this was taken from Introduction to Physical Gas Dynamics by Vincenti and Hypersonic and High Temperature Gas Dynamics by Anderson. There were some relations which were mentioned in the lectures like mean and mean velocity, most probable velocity, root mean square speed, and some of these were derived using the kinetic theory of gases, but we will derive this using the Maxwell distribution. So we have already seen that probability that a given molecule has speed between c and c plus dc is given by chi c equal to 4 pi c square m upon 2 pi kt to the power 3 by 2 e to the power minus m upon 2 kt into c square. First we will find what is the most probable speed. So what is the most probable speed? Which has the maximum probability. So this gives the probability. So we have to find the speed at which this probability is maximum. So what is the condition for maximum? Its derivative with respect to its speed should be 0. So d chi c upon dc equal to 0. Now we will take its derivative. So if we see this part is independent of c. So we can take it out of derivative also. This we have taken out of derivative, and after the term we can write inside the derivative c square e to the power minus m upon 2 kt c square equal to 0. So this term will go on the right hand side, so we have to find this term, this dc c square e to the power minus m upon 2 kt c square, it should be equal to 0. Now we will take its derivative. So first term will be 2c into e to the power minus m upon 2 pi, so this is 2 kt, c square minus m minus this c square will be as it is. This is e to the power minus m upon 2 kt c square, derivative will be m upon 2 kt e to the power minus m upon 2 kt c square into 2c equal to 0. In this both term, what are the common? 2c into e to the power minus m upon 2 kt c square, 2c into e to the power minus m upon 2 kt c square. If we take it common, then it will become 2c into e to the power minus m upon 2 kt c square into this term. This term will go on right hand side, so it will become only 1 minus m upon 2 kt c square equal to 0. This we can also write as 1 equal to m upon 2 kt c square, and so now we will get c square equal to 2 kt upon m, which will be c equal to under 2 kt upon m. This c is c most probable. This kym will give the r, where this r is specific gas constant. So we have seen it. the most probable velocity or speed. Now we will see average speed. So how is the average speed given by? It is given by c bar equal to integration 0 to infinity c chi c dc. This chi c gives the probability of velocity between c and dc, and if you want to take its average, then you have to multiply it by c and take its integration. So we will put the value of chi c here. What was the value of chi c? 4 pi c square, and this c will multiply, so it will become c cube. 4 for integration 0 to infinity 4 pi c cube m upon 2 pi kt to the power 3 by 2 into e to the power minus m upon 2 kt c square dc. This 4 pi will take it out, and in this one you will take out only under root m upon 2 pi kt. This under root m upon 2 pi kt we took out, and inside it became m upon 2 pi kt. This pi, 1 pi which we have taken out, and this 1 pi will cancel. So it will become 4 m upon 2 pi kt to the power 1 by 2 integration 0 to infinity m upon 2 kt c cube e to the power minus m upon 2 kt c square dc. Now you will understand why we have kept this term inside. Now let's assume z equal to m upon 2 kt c square. This power e to the power, what was the term with the power of e? We are taking it as z. So m upon 2 kt c square. So dz will become 2m upon 2 kt c dc. Here you will also can see that m upon 2 kt c dc will be equal to dz upon 2. So this term was same as it will remain same as it is. So c bar equal to 4 m upon 2 pi kt to the power 1 by 2 integration 0 to infinity. This c cube can be written as c square into c. So 1c and this m upon 2 kt dc will be written dz upon 2 and the c square can be written as, from this, c square can be written as 2 kt z upon m. So we have replaced it 2 kt z upon m, and it is power this term minus 2 kt c square, it will become minus z. This 2 will cancel, and we will take this kt upon m outside. So if we take this kt upon m outside, you see this 2 pi will remain as it is, and this kt upon m will multiply this by this under root m upon kt, and will become 4 under root kt upon 2 pi m. This 4 also, if we take it inside, it will become 16. We divided by 2, it will become under root 8 kt upon pi m. Okay, and this integration which will remain integration 0 to infinity z e to the power minus z dz. Now we will use integration by part. This is first function, this is second function. If someone joined, so what I was doing, I was deriving the average speed of particles using the Maxwell distribution. So this speed is given by c bar equal to integration 0 to infinity c chi c dc. Here this chi c is nothing but probability that a given molecule has speed between C and C plus dc, and it is given by this relation chi c equal to 4 pi c square m upon 2 pi kt to the power 3 by 2 e to the power minus m upon 2 kt c square. So in this relation I substitute chi c, taken out the constant term, and we got this integration. So in this integration I substituted this m upon 2 kt c square. What was in the power of this e, I taken it as z and substituted it here. So I will get this integration as finally 4 under root kt upon 2 pi m integration 0 to infinity z e to the power minus z dz. Here now we will do the integration by parts. This is the first function, this is second function. So it will be first function into integration of second function. Its integration is minus e to the power minus z minus differentiation of first function into integration of second function. Its integration is minus e to the power minus z. So minus minus will become plus here. Integration differentiation of this function is 1. So it will e to the power minus z dz. You can try doing that yourself. Now in this term, if you put this infinity, e to the power minus infinity will become 0. If you put it 0, then z will be 0. So this term will be 0 only. The second term integration will become minus e to the power minus z, and we have to put limit 0 to infinity. If you put the limit, and here one more thing I have done, this term we got outside under root 8 kt upon pi m. So we know that k by m equal to r, a specific gas constant. I substituted it here, and when we put the limit, then we will get minus 1 upon e to the power infinity plus 1 upon e to the power 0. E to the power infinity is infinity, 1 by infinity is 0, and e to the power 0 is 1. So this term will become 1. So we will get the velocity as under root 8 RT upon pi. So we got average speed as under root 8 RT upon pi. Is there any doubt till here? If no, then I will derive the expression for root mean square speed using this Maxwell distribution. So how is the root mean square velocity given by? It is given by root of average of square of velocity. So first we will find the average of square of velocity or speed, which is given by integration 0 to infinity c square chi c dc. This is for finding the average of velocity. Now we will put this expression for chi c. So chi c was 4 pi c square, and this c square becomes c to the power 4 m upon 2 pi kt to the power 3 by 2 e to the power minus m upon 2 kt into c square dc. Here I will take all the constant term outside. So it will our constant term 4 pi m upon 2 pi kt to the power 3 by 2, and inside the integration it will become 0 to infinity the c square into e to the power minus m upon 2 kt c square dc. Yes. So now we have to find this integration. For a second, let's take it as I equal to integration 0 to infinity c to the power 4 e to the power minus a c square dc. Now here we have written a equal to m upon 2 kt, and this integration is given by 3 by 8 pi upon e to the power 5 whole power 1 by 2. This integration I will tell just after this. Currently take it as this value. So this I value will be 3 by 8 under root pi upon a to the power 5, where a is m upon 2 kt. So in this expression, we will substitute the value of this integration. We will get 4 pi m upon 2 pi kt to the power 3 by 2. Here we are writing this m upon 2 kt to the power 3 by 2 and pi to the power 3 by 2 separately, because this is a, nothing but a. And the value of this integration is 3 by 8, pi to the power 1 by 2 and a to the power 5 by 2. Here this pi to the power 1 by 2 and this pi combined will cancel with this term. This 4 will cancel it and become 2. And this term is a. So a to the power 3 by 2 and this is a to the power 5 by 2. So after solving it will become 3 by 2 a. If we put the value of a, then we will get it 3 kt upon m. And we know that k by m is nothing but r, so it will become 3 rt. And if we take its root, then it will become root mean square velocity or speed equal to under root 3 rt. So this is a derivation for that root mean square speed. Is there any doubt till now? If no, then I will tell about that integration which I will use this directly here. So now I will solve this integration first. So this integration is in terms of this expression I and a equal to integration 0 to infinity x to the power n e to the power minus a x square dx. And in our expression value of n was 4. So here I4a will become integration 0 to infinity x4 e to the power minus a x square dx. It is similar to this only. If you take its derivative with respect to a, you can see that d I n a upon dA equal to what? If you take its derivative with respect to a, this minus x square will go as a derivative, so you will get minus I n plus 2a. You can see the derivative also, d I n a upon dA. You can apply the Leibniz rule also, so it will become integration 0 to infinity dy dA x to the power n e to the minus a x square dx. This x square is constant with respect to a, so we will get integration 0 to infinity x to the power n, and its derivative will be minus x square e to the power minus ax square dx. So it will become minus integration 0 to infinity x to the power n plus 2 e to the power minus ax square dx, which is nothing but I n plus 2a. So using these two relations, we will find this derivative, this integration. First we will find what is I1a, because if we wanted to find I4a, we can use the relation for I2a. If we want to find I2a, we can use the relation for I0a. Similarly, if we want to find for I3a, we can use for I1a. So if we know the value of I0a and I1a, we can find all other value of integral. So we will first find I1a. So I1 is a is given by integration 0 to infinity x e to the power minus a x square dx. We have only put x equal to 1 here. Now let's assume ax square equal to z. So 2ax dx will become dz. So we can write a dx equal to 1 upon 2a dz. My 2 and z are somewhat similar, so pay attention to what I am speaking also. So we'll substitute this value here. So I1 here will become 1 upon 2a. This x dx is replaced by 1 upon 2 dz. So 1 upon 2a will come out. Integration 0 to infinity z e to the power minus z. Oh, sorry, here it's not z here. This x dz will be 1 upon 2a dz. So 1 upon 2 dz, and this e to the power minus z. So it will become integration 0 to infinity e to the power minus z dz. If we do its integration, you can see before also. Integration 0 to infinity e to the power minus z dz. Its integration was what? It was 1. Its value was 1. So I am not solving it. You can directly take it as 1. And it will come 1 upon 2a. So now we got the value for I1a, which is 1 upon 2a. But we need I0a also. So we will find I0 equal to integration 0 to infinity e to the power minus ax square dx. Only put the value of 0 here instead of in place of n. It cannot be solved in a normal method, so we will take its square. So it can be written as multiple of two integral. Only variable we have changed. One is with respect to x, one is with respect to y. So I naught square a equal to integration 0 to infinity e to the power minus ax square dx, and 0 integration 0 to infinity e to the power minus ay square dy. These both can be written together as integration 0 to infinity double integration e to the power minus a x square plus y square dx dy. Now we will change it to polar coordinate. So in polar coordinate, dx dy can be written as r dr d theta, and x square plus y square can be written as r square. So this I naught square a will become integration 0 to pi by 2 d theta. Why? Because if you see in the coordinate system, if x is from 0 to infinity and y is from 0 to infinity, only one coordinate we have taken. So in terms of this theta, it will be from 0 to pi by 2. So integration 0 to pi by 2 d theta we have taken separately because it is independent of pi by 2, independent of theta. And second term will be 0 to infinity. This dx dy is replaced by r dr d theta, and this e to the power minus a r square will come. And this is nothing but, if you compare I1a, and this integration will become pi by 2. So ultimately it will become pi by 2 I1a, and value of I1a was 1 by 2a, so it will become pi upon 4a. That's why we have found first I1a, because we needed it for I0a. So I0 will become 1 upon 2 under root pi upon a. So how to find I2a? We will use the relation, the derivative relation. If I2a will become equal to minus d I0a upon dA. Replace n by 0 here. So I2a equal to minus d I0a upon dA equal to, if we take its derivative with respect to a, it will become minus, there is already minus, so if we take its derivative, this pi is constant, 2 is also constant, and this is a. a to the power minus 1 by 2. So its derivative will be minus 1 by 2 a to the power 3 by 2. So minus, and we already have, they have minus, so we will get 1 by 4 pi upon a to the power 1 by 2. Similarly for I4a, we have to take its derivative. It will become minus d I2a upon dA. If we take its derivative, we will get 3 by 8 pi upon a to the power 5 under root pi upon a to the power 5. This is only we have used here before for the root mean square velocity. Is there any doubt till now? If there is no doubt, then we will see one graph also. This is for speed distribution function versus velocity c upon under root 2 kt upon m. So if you plot this plot, it will come like this. It is changing. So at each velocity will have different probability, and this where it is becoming maximum, it is good. It is most probable velocity given by CMP. If you see the C bar value, it was under root a upon pi RT. Here also you can see under root 8 upon pi RT. And if you see the value of 8 upon pi is approximately 2.55 RT. The C most probable is under root 2 RT, and this root mean square velocity is under root 3 RT. So that's why this most probable velocity is the lowest. Mean velocity is greater than this and lower than root mean square velocity, and root mean square velocity is highest. Is there any doubt till now? If there is no doubt, then we will see one problem. Sonic speed A and most probable speed CMP in air is approximately related as follows. Option A equal to 0.84 CMP. Option B, CMP equal to 0.91 A. Option C, A equal to 0.71 CMP. Option D, A equal to 1.07 CMP. So CMP we found already under root 2 RT. C most probable speed, and phonic speed is given by under root gamma RT. So if you want to find the relation of A upon C and P, it will become under root gamma upon 2. Here gamma, generally for air, gamma equal to 1.4. If there is nothing is given, you can take gamma equal to 1.4 for air. So it is 1.4 upon 2, which will be under root 0.7. And value of under root 0.7 is nothing but 0.8366, which is approximately 0.84. So option A is the correct one. Is there any doubt in this question? Okay, no doubt. Then we see the next problem. The single particle collision frequency in a given gas is 2 into 10 to the power 16 collisions per second. When the pressure and temperature are both increased by a factor of 4, what is the collision frequency? So how to solve this problem? So first we need to know the relation between collision frequency, single particle collision frequency, and temperature and pressure. So if you know the relation, you can directly use generally Z is directly proportional to P upon under root T. You can directly use this relation to find it, but here we will first derive how we got this relation. So for a single species gas, single particle collision frequency is given by Z equal to n pi d square c bar upon under root 2. This is given for uh, if we are considering the relative velocity between the particles. If you don't consider the relative velocity between the particle, then this root 2 will not be there. This root 2 is due to effect of that only. And in this formula, this n is number of particles per unit volume, and c is the mean speed, this is number of particles per unit volume, and t is related to sphere of influence. Of a particle. Or called radius of influence. Here we know that what is the mean speed, that is given by under root 8 kt upon pi r. So we will substitute it. So we got relation equal to this z equal to n upon root 2 pi d square under root 8 kt upon pi r. So we know the equation of a state, which is given by P equal to n kt. P is the pressure here, K is the Boltzmann constant, and T is the temperature, and N is the number of particles per unit volume. From here we can find N equal to P upon Kt. We will substitute this value in the formula of Z. So if we substitute this value of N, we will get Z equal to P upon under root 2 kt pi d square under root 8 kt upon pi r. Here we will take this P and root T separately. So this P will come here. This T and root T, if is simplified, will come 1 upon root T. This d square will be here. Now we will take this root 2 and pi inside this root. So it will come under root 8 kt pi square upon 2 pi m. So this 5, 1 5 will cancel, and this 2 will cancel this 8 and become 4. So it will become under 4 pi. Sorry, this key I have already taken outside. 8k upon, sorry, 4k upon this k also I will take inside. This it will become k square. 1k will cancel, so it will become under 4 pi upon km, or p upon root t d square into 2 under pi upon km. So what we got, z is that equal to p upon root t. So in the problem, what is given that pressure and temperature are both increased by a factor of 4. So if initial, let's say initial properties was meanwhile 1, so if pressure was T1 initially and temperature was T1, and in the later they are increased by factor of 4, so pressure T2 become 4T1 and temperature T2 become 4T1. So if we take the ratio of this collision frequency, then Z2 upon Z1 equal to P2 upon P1 under root T1 upon T2, and this relation only. This P2 and P1 is what? 4, and T2 and T1 is also 4. If we substitute, we will get Z2 upon Z1 equal to 4 upon under root 4. If under root 4 is 2, so 4 upon 2 is 2. So Z2 will be 2Z1. And part of the value of Z1, 2 into 10 to the power 16. So multiply it by 2 and it will become 4 into 10 to the power 16 collisions per second. This is the answer. Now we will see another question. This is based on equilibrium constant for chemical reactions. The equilibrium constant based on concentration Kc is related to equilibrium constant based on partial pressure Kp using the following relationship. Mu I is stoichiometric mole number for the reactants and product with negative and positive sign respectively. R is the universal gas constant here in the equation. So there are 4 options. Kc equal to under root Kp to the power sigma I mu I. Kc equal to 1 upon RT Kp to the power sigma I mu I. Kp equal to 1 upon under root Kc to the power sigma I mu I, and Kc equal to 1 upon RT to the power sigma I mu I Kp. So for this one, first we have to see what is the chemical reaction. So let's say there was one chemical reaction which is given by mu1 dash A1 plus mu2 dash A2 plus so on mu dash K AK, and product will be mu dash K plus 1 AK plus 1 plus mu dash K plus 2 AK plus 2, and so on mu J dash AK. So currently in this chemical reaction, all this stoichiometric coefficient are positive. Now we will take everything on the right hand side. So we will get if we take everything on the right hand side, then this term will get the negative value also. So we can write this whole equation as sigma mu I I equal to 1 to j equal to 0. Here this mu I can take the positive and negative value both. So these are the stoichiometric mole number. Now you will see what is the relation between Kc and Kp. If you know the relation directly, this answer is very straightforward. But here we will write that relation. That Kp is the equilibrium constant based on partial pressure, and Kc is the equilibrium constant based on concentration. We have already seen in the last week the formula of this Kp is given by Kp equal to pi I Pi to the power mu I. Here this pi is the product and Pi is the partial pressure of ith species, and mu I is the stoichiometric coefficient of ith species. Now we will use the equation of state. Equation of state in terms of concentration is given by Pi equal to Ci R bar T. For differentiate between a specific gas constant and universal gas constant, I am using bar on top of R for universal gas constant, so that there is no confusion. So Pi equal to Ci R bar T. So if you substitute this value of Pi, then we get Kp equal to pi I Ci. This Ci here in the formula there is Pi to the power mu I. So here also it will become Ci R bar T to the power mu I. We can separate the Ci term and R bar T term, so it will become Ci mu I and R bar T to the power mu I. As this R bar T this also we can, as it is product only, so this term we can write this as pi I Ci mu I into pi I R bar T to the power mu I. Now what this second part means is that this R bar T mu 1 into R bar T mu 2 and so on. So if we take it together, it will become R bar T to the power mu 1 plus mu 2 and so on, which is nothing but summation. So this term will become R bar T to the power sigma mu I, and therefore term is pi I Ci mu I. This is nothing but equilibrium constant based on concentration Kc. So we get Kp equal to R bar T sigma I mu I Kc, or we can take this term left hand side, and we will get Kc equal to 1 upon R bar T to the power sigma I mu I into Kp, which is nothing but option D. Kc equal to 1 by RT sigma I mu I Kp. Here this R, they are using R for universal gas constants, and I am using R bar. Generally you will see that normal R is a specific gas constant, and italics R is universal gas constant. This whole lecture series, generally it is used like this. So here you can see this R is italics. So you can differentiate like this also, if you are getting some confusion in the problem. Okay, so now we'll see the next problem. This is the, you can say, conceptual question. A certain mass of gas is vibrationally excited through irradiation of an appropriate wavelength. The following statement or statements H or are true regarding the events which follow. Through molecular collisions, the excited gas particles will exchange the excess vibrational energy with the translational and rotational energy modes of the gas. Option B, vibrational energy will increase with time. Option C, vibrational energy will decrease and approach its equilibrium value, which is greater than the initial vibrational energy. Initial equilibrium vibrational energy. The gas temperature will increase as vibrational energy decrease, while translational and rotational energy increases. So in this one, multiple options are true. Now first we will see what happens when molecular collisions happen. If particles are vibrationally excited and molecular collisions happen, then the whatever excess amount of vibrational energy they have, it will be transferred to translational and rotational mode of gas. So this option A is true. Now what will happen that some energy of the gas is transferred to translational and rotational energy mode of the gas. It will increase the translational energy and rotational energy. So if translational energy increases, the temperature is mainly given by translational energy. It is proportional to translational energy only. So if translational energy increases, it means temperature increases. So if temperature is increasing, so you can see that this option, the gas temperature will increase as vibrational energy decreases. So some energy of this vibrational energy is transferred to rotational and translational energy mode. So E translational increases, E rotational increases, but E vibrational will decrease as collisions happen. So these are related to temperature. This is related to temperature. So temperature will increase. Now what we got? Vibrational energy will decrease. This energy will increase and temperature will increase. So this fourth option you see, the gas temperature will increase as vibrational energy decreases, temperature increases, while translation and rotational increases. So this is also correct option. Option B you see, vibrational energy will decrease with time. We already saw it will decrease with time, so this option B is wrong. Now what happened that if this mass of gas is left alone, that after time what will happen, this vibrational energy will transfer its excess energy to translational and rotational mode, and it will decrease and it will approach its equilibrium level. So there is a plot also. Here equation is not mentioned, so I will mention the equation also. So this is for equilibrium. If E vibrational equal to E vibrational equilibrium equal to h nu by kt upon e to the power h nu by kt minus 1 RT. This is for this plot, and for this plot will be d e by 2. This is for non-equilibrium equal to 1 upon tau e vibrational equilibrium minus e vibrational. This is for vibrational non-equilibrium. So I told that its energy will decrease. This e vibration 0 is for time t equal to 0. So as time passes, this vibration energy will transfer to rotational and translational mode, and this energy will decrease and it will move to equilibrium position. And what happened to vibration energy? You can see this vibrational energy, equilibrium vibration energy depends on temperature. So as translational mode energy increases, this vibration energy will also, equilibrium vibration energy will also increase, and it will reach a final equilibrium value. So what happened that this was the initial equilibrium vibration energy, but final equilibrium vibration energy is greater than this value. So the vibration energy will decrease to and approach its equilibrium value. This is also 2, which is greater than initial equilibrium vibration energy. So the equilibrium value which it is approaching, it is greater than initial equilibrium vibrational energy. So this is also 2. So its correct answer U, C, and D. If K, now we will see the next problem. If K10 is the vibrational rate constant for transition from I equal to 1 to I equal to 0, then from quantum mechanics, the rate constant for higher energy level transition can be expressed in terms of K10 using the following rule. This is from quantum mechanics. So Ki I minus 1 equal to I K10. So Ki I minus 1 means that the transition is happening from level I to I minus 1. In this the transition is happening from I to I minus 1 level, and it is given by I K1, 0. Using this rule, the value of K4, 3 upon K3, 2 is given by. So K4, 3 equal to 4 K1, 0 from this rule only, and K3, 2 is given by 3 K1, 0. If we take ratio of these two, K4, 3 on K3, 2, it is nothing but 4 by 3. In the option, this is option C. This will be the answer. Now we will see the next problem. Vibrational excitation and chemical changes in a gas occur due to molecular collision as well as relative interactions. So you already know that what was the collision for. The collision is the one which is responsible for vibrational excitation and all the chemical reactions which happens in the system. And you all also know that there are always distance between two molecules, which is generally given by mean free path. average value of the uh, sorry there are always distance between two molecules, and it takes time for molecules to travel. So for the collision also it takes some time, and for the successive collision there is it is given by distance by mean free path. So a molecule has to travel by mean free path for the one collision to happen, and it takes multiple collision for this chemical reaction or vibrational excitation to occur. So it takes some time for these changes to happen, and this time is referred to as, there are four options here: vibration excitation time, response time, delay time, excitation relaxation time. So this term is called the relaxation time. It is for both chemical changes and vibration excitation. Okay, so now we have solved some problems. Now we will see what is the chemical non-equilibrium. So in chemical non-equilibrium, the due to the collisions, particles transition from one vibrational level to another vibrational level, and due to which the number of particles in one energy level changes. So that change only we will keep the track. So first we will see the energy levels. Let's say this is the ith energy level, this is ith plus 1, this is I minus 1. Its energy is epsilon I, and its epsilon I plus 1, this is epsilon I minus 1. Before that, one thing I will note: the energy of level is given by epsilon dash I equal to I h nu 1 plus 1 by 2. Oh, sorry, h nu I plus 1 by 2, and its zero level energy is given by h nu by 2. So the energy above the zero level is given by epsilon I equal to epsilon dash I minus epsilon g1, which is nothing but I h nu. So here energy is written for above the zero level. So in what way transition can happen for state energy level I? The particles can go from this energy level to I plus 1 or go to I minus 1. This is due to which the number of particles in energy level I will decrease, and the particles can also come from I plus 1 level to I level I, and it can also come from level I minus 1 to I, due to which the number of particles will increase. So from jumping of the particle from I to I plus 1 will increase the particles, and from I minus 1, sorry, I to I plus 1 will decrease the particles, I minus 1 to I will increase the particles, I plus 1 to I will decrease, and I plus 1 to I will increase, and I to I minus 1 will decrease. So this transition happens due to molecular collisions only. This is vibrational non-equilibrium. So this transition happens due to collisions only, but not all collisions will be responsible for this transition. So only some collision will be responsible for the transition of one particle from one energy level to another energy level. And this probability of collision which will be responsible is called P. Is given by P, and it is called transition probability. So if let's say there is one particle in ith level and it will have molecular collision with another particle and go to I plus 1 energy level. So the probability of the particle going from ith level to I plus 1 is given by P I plus 1. And we also know that Z is the collision frequency of a particle. Per second. So what will Pi I plus 1 into Z will give? It will give the number of transitions per particle per second. But in the ith level there are Ni particles. So if we multiply this by Ni, it will give number of transitions, total number of transitions per second. So if let's say this number of transitions are happening from I to I plus 1, it means this number is decreasing in the ith level. Let's say Ni is the number of particles in ith level, then change in number of particles in the ith, rate of change of number of population in the ith level will be equal to, there are two ways particles can increase. So first we will write the from I plus 1 to I, the particle will, it will increase from I plus 1 to I, Z and I plus 1, and I minus 1 to I also it will increase. So this will increase number of A and I. So this is rate of increase of Ni. It will be minus P I comma I plus 1 Z Ni minus P I minus 1 Z Ni. This will be the rate of decrease of N. Now for the simplification we can take one constant K, which is vibrational rate constant. It is given by T I plus 1 I into Z is given by K I plus 1 I. This is the bidirectional weight constant. This is for transition from I plus 1 to I. Similarly, for other transition, it can be written similarly. So we will get dni upon dt equal to k I plus 1 I and I plus 1 plus k I minus 1 I and I minus 1 minus k I plus 1 and I minus k I minus 1 and this is called the master equation for vibrational excitation. Oh, sorry, vibrational relaxation. Master equation for vibrational relaxation. Now let's consider that gas is in equilibrium. But before that, first we will see that take that let's assume that gas is in equilibrium. So Ni star upon Ni minus 1 star. It will be given by, you see the formula from Boltzmann distribution, it will be given by Gi for bidirectional. This degeneracy will be equal, so it will become given by e to the power minus epsilon I upon kT upon e to the power minus epsilon I minus 1 upon kT, which will be e to the power minus epsilon I minus epsilon I minus 1 kT. You substitute the value of epsilon I, will get minus I h mu minus I minus 1 h mu upon kT. And the difference of these two will be given by e to the power minus h mu upon kT. And as it is in equilibrium, so what will happen? Let's say there are two levels I and I minus 1. We are getting some particle from I to I minus 1, and we are getting some particle from I minus 1 to I. So whatever transition these happen, they should counterbalance each other. Counterbalance each other, only then there will be vibrational equilibrium. So this principle is called principle of detailed balancing. So what is the transition from I to I minus 1? It is k I minus 1 and I star. It will be equal to k I minus 1 to I and I minus 1 star. One thing is to note that this vibrational rate constant we are taking the same because it will not depend on the number of particles. So the ratio of k I minus 1 comma I will be given by ni star upon ni minus 1 star k I minus 1 and ni star upon ni minus 1 star is given by e to the power minus h upon kt k I comma I minus 1. Similarly, for k I2 I plus 1 will be given by e to the power minus h upon kt k I plus 1 comma I. We got these two relations, and from the quantum mechanics there is also one relation which says that if all rate constant for the higher level energy level can be written in terms of transition from I equal to 1 to 0. So k I to I minus 1 equal to I k 1 comma 0. This we have seen in the previous problem also. This k I minus 1 equal to I k 1 0. Similarly, k I plus 1 comma I equal to I plus 1 k 1 comma 0. So now similarly we will get the relation from this k I minus 1 I k I minus 1 I, it is nothing but e to the power minus h upon kt, and this k I minus 1 will be written as I k 1 comma 0. Similarly, k I plus 1 equal to e to the power minus h upon kt, and this k I plus 1 I will be given by I plus 1 k 1 comma 0. So we got all these four vibrational rate constant in terms of k 1 0. Now we substitute everything in this master equation. So we will get dni upon dt equal to ki plus 1 comma I k I plus 1 comma I substituted by I plus 1 k 1 comma 0 and I plus 1 plus e to the power minus h nu upon kt I k 1 comma 0 and I minus 1 for the second term, ki minus 1 comma I and I minus 1, ki minus 1 comma I its value n into n minus 1 minus I k 1 comma 0 and I minus e to the power minus h nu upon kt I plus 1 k 1 comma 0 and I. So k 1 comma 0 you can take common in everything. It will come minus I and I plus I plus 1 and I plus 1. In this two term you can take e to the power minus h nu upon kt term constant. It will come minus I plus 1 and I plus I and I minus 1 this is the equation which we got for rate of change of population of the ith level. Rate of change for population of ith level. So generally we are more interested in vibrational energy. So we will find the rate of change of vibrational energy. So vibrational energy is given by sigma epsilon I and I equal to 1 to infinity. Epsilon I is given by, and this vibrational energy also we have taken above the zero level. So epsilon I is given by I h nu into ni. This h nu is constant, so it will come out. So vibrational equal to h nu sigma I and I equal to 1 to infinity. This is one equation. From this we will get one more thing. Sigma I and I equal to 1 to infinity equal to E vibrational upon h nu. We will have its use later. Now we will take its derivative. So we will get d E vibrational upon dt equal to h nu sigma I equal to 1 to infinity I dni upon dt, because all these terms are independent of time. Now we will substitute this dni upon dt inside here, and this k10 is constant and also independent of temperature of time, so we take it out also. So we get h nu k 1 comma 0 sigma I equal to 1 to infinity this I will multiply in each term. So we get minus I square ni plus I plus 1 and I plus 1 plus e to the power minus hp upon kt minus I plus 1 ni plus I square and I minus 1. Now we have to find the summation. First we will find the summation of these first two terms. So this equation you can write as equation A. So for this part, first we will find summation for this part. Sigma I equal to 1 to infinity minus I square ni plus I plus 1 and I plus 1 so if we separate all these parts, then we get sigma I equal to 1 to infinity minus I square ni plus sigma I square ni plus 1 or keep it like that one. I equal to 1 to infinity I plus 1 and I plus 1. For this term, we will substitute I plus 1 equal to s. So for I equal to 1, s equal to 2. So we will get this term equal to sigma I equal to 1 to infinity minus I square ni plus sigma s equal to 2 to infinity. It will be I equal to s minus 1. So we will get s minus 1 into s ns. Now we will separate this term. We will get minus sigma. Here we will write for I equal to 1 and I equal to separately. So we will get for I equal to 1, it will be minus n1 minus sigma I equal to 2 to infinity I square ni plus sigma f equal to 2 to infinity f square ns minus sigma f equal to 2 to infinity s ns. This you see both terms are same only this index is different, so these two will cancel and this terms is nothing but if you put the value of f equal to 1 here minus n1, it is nothing but terms of this one. So we can write these two together as minus sigma I equal to 1 to infinity I n. If we take the summation of these, then this term is common, so it will take outside. So we will take the summation of these terms. Which is sigma I equal to 1 to infinity minus I plus 1 and I plus I square and I minus 1. This also will separate. sigma I equal to 1 to infinity minus I plus 1 and I plus sigma I square and I minus 1, I equal to 1 to infinity. Here we will take, for this term we will take I equal to s minus 1. So I equal to 1 will be s equal to 2. So we will get minus sigma s equal to 2 to infinity s minus 1 into s and s minus 1 plus sigma I square and s minus 1. This also we will write for, sorry, this is I minus 1. This will also write for I equal to 2 to infinity. For 1 we will take out, so it will be plus and I minus plus and 0. This term also we can write with 0 also. So if we write it, sigma I equal to 0 to infinity I and I. It does not matter if I equal to 0, this term will be 0 only. But here we are getting into it, that's why I will trim it. We will separate this term, so it will come minus sigma s equal to 2 to infinity s square and s minus 1 plus sigma s equal to 2 to infinity s n minus 1 plus sigma I equal to 2 to infinity I square and f 1 minus I minus 1 plus n0. These two terms are same, so they will cancel, and this term can be written as sigma s s n minus 1 plus n0. We will write, we will come back again to I, so s, we will substitute s minus 1 equal to I. So it will be sigma I equal to 1 to infinity s I plus 1 I plus 1 and I plus n0. This can be written together, sigma I equal to 0 to infinity I plus 1 and so this simplification we will substitute for that equation number A. So we will get d by vibrational upon dt equal to h k1 comma 0 sigma I equal to 0 to infinity minus I and I. First term we got minus I and I. These two terms we got minus I and I. For the second term, it was plus E minus h mu upon kt, and we got I plus 1 and I. We can separate this term and we will get h mu k1 comma 0 we write this term separately, sigma I equal to 1 to infinity minus I and I plus e to the power minus h mu upon kt I and I plus e to the power minus h mu upon kt and I. These two terms we can write together, so it becomes h mu k1 comma 0 and this summation we will also write separate, e to the power minus h mu upon kt sigma and I one thing, after we have done the summation, this all summation becomes from I equal to 0. So this is I equal to 0 to infinity minus this term we have written currently here. Now this term will be minus 1 minus e to the power minus h mu upon kt sigma I and I equal to 0 to infinity. Now sigma and I equal to 0 to infinity is nothing but n, total number of particles, and before we have found sigma I and I equal to 0 to infinity is nothing but E bidirectional upon h mu in the starting itself. Here we substitute it here. So we'll get dE bidirectional upon dt equal to k1 comma 0. This h nu also will take it inside. H mu and e to the power minus h mu upon kt minus 1 minus e to the power minus h mu upon kt E bidirectional upon h mu. If E by 1 minus e to the power minus h nu upon kt, I will take it outside. So k 1 comma 0 1 minus e to the power minus h nu upon kt. I will get h nu n e to the power minus h nu upon kt upon 1 minus e to the power minus h nu upon kt minus e vibrational. Oh, sorry, this h nu I multiply inside, so there will not be this h nu here. It is not working, so okay, this h nu will not be here. Now this e to the power minus h nu, we can take it in the denominator, so we will get k 1 comma 0 1 minus e to the power minus h nu upon kt h nu n upon e to the power h nu upon kt minus 1 minus e by this. Now we can, if we see this term, we can divide and multiply it by kt. So this nkt will give rt. And there was one more thing. This equation is nothing but equation for E vibrational equilibrium. So we can substitute this term by E vibrational equilibrium, and hello. And we will define one relaxation time tau equal to 1 upon k 1 comma 0 1 minus e to the power minus h nu upon kt. So our equation d E vibrational upon dt will become E vibrational equilibrium minus E vibrational upon tau. This equation is called vibrational rate equation. This equation only I have plotted before. I found the plot of this before. This one. This was the plot only. So we will end our class here, and most of the things I have taken is from Hypersonic and high temperature gas dynamics and Introduction to Physical Gas Dynamics by Vincenti. If you have any doubt in class, if there is no doubt, then I will end today's class. Is there any doubt? No, then I will end today's class.